Alright, nerds, so we're still kicking along in acids and bases, or acidic environment, but we still need to focus on equilibrium for just a little bit longer before we can start applying it to all of our other experiments. So here we're going to focus on equilibrium, changes to equilibrium, which we've already covered once, and we're now going to look at applying it to a certain situation. So what's the point of today? Today the whole point is to explain what will happen to a system in equilibrium with and apply that to a specific case, which we've already looked at. In this case, it's going to be the degassing, also, opening up a can of soft drink and releasing the CO2. All right, you need to remember essentially that we'll go over this in a tick, but when there is more carbon dioxide, the reaction, the hydrogen ions in the water also increase. So as we put more carbon dioxide in the water, that's here, we then get more of this, and that makes it more acidic. Okay, and also that's how we know something has an acid in it. All right, now I'm just going to change my pen to that bad boy. All right, so dissolved carbon dioxide. We're just going to have a quick look at the reactions involved. Now, first, we need 4 equilibrium reactions. Usually we'll let you summarize it, but in this case we want 4 equilibrium reactions. So first, we are using this symbol here instead of that one. And the only reason is there is no key there's no ASCII key for the double arrows that we need to use. We'd have to save it as a picture and it's just too time consuming. So anyway, carbon dioxide is a gas, dissolves into an aqueous solution. Cool. The next step is it mixes with the water to create carbonic acid. Then this dissociates into hydrogen ion plus hydrogen carbonate ion, and the hydrogen carbonate ion then dissociates further into a hydrogen ion plus a carbonate ion. Now, while we're at it, it's very important to remember there is one gas, okay, that will become very, very important later on, and there is everything else is aqueous except for this. Now, water, of course, you can't increase the concentration of water. It's the medium, so if that's in our reaction, all it does is it decreases the concentration of everything else, which is kind of the same deal, but mathematically speaking, it all works out. So an equilibrium to the shift to the left or the right leads to a change in concentrations of reactants and products. Now, if you do it to one reaction, for example, if we do it just here, if we increase the concentration, that will then cause an increase in all of the others. So if we increase the concentration of carbon dioxide here, what that means, or even here, what that means is, so carbon dioxide is a gas, we inject some in, that will then shift, so it wants to go to an equilibrium, which means it then moves to here. So it produces more of that, which then shuffles all these further along. Basically, what this means is that can happen at any stage. Okay, so a decrease in the pressure above causes a shift to the left. This results in a decrease in the pH. So all the other things, everything else shifts to the left as well. Now, we might actually have a look at that in class practically, we'll do a couple more things. All right, so change in temperature. So let's look at the 3 things, the 3 principles, 3 changes according to Le Chatelier's principle that we are focusing on for our unit. So if the forward reaction is exothermic, basically an increase in temperature causes the system to shift in the reverse direction. Okay, so if it's an exothermic, so it's A plus B gives you A, B plus heat, okay? Then if we increase the temperature, so we're essentially adding more of this, not really a reactant, but it's part of the equation. We add more to that, which will cause the reaction to shift in that direction. Okay, so we get, anyway, if the forward reaction is endothermic, basically an increase in temperature causes the system to shift in this direction. So if it's actually H plus, and we get rid of that. We add more heat, it will cause it to shift along this way. So if we take the temperature away, the opposite's also true. So just remember what happens if we increase temperature for both an exothermic and endothermic, and you can apply it backwards. So let's apply this to CO2. All right, CO2 is dissolution of CO2 is an exothermic reaction. All right, so an increase in temperature causes the reverse reaction. So if we go back to our CO2 as a gas, and then over here, CO2 aqueous. So if we do that, right, so if we increase the temperature, that means it forces off that way, okay, shifts off in that direction. If we decrease the temperature, it will go that way. Now, if you want to think of this as a global issue, when we look at global warming as a problem, as the, so here's your ocean with its CO2 molecules. As the oceans heat up, these go off into the atmosphere. As they go into the atmosphere, they cause the atmosphere to heat up further, trap heat further, which brings heat down into the oceans, which then causes more to dissolve, to leave solution. So that's a real world problem for that, beyond just your can of soft drink going flat. Changing concentration. All right, so if we change in concentration, essentially an increase in concentration of one of the reactants or a decrease of one of the products causes it to shift forward, okay? So if we've got our CO2, really should have had this for all of them. So if we put more CO2 in, what's going to happen is, so if we put more CO2 in, the reaction will shift this way to our CO2 aqueous. Now, if we decrease the concentration, so we're able to, we're using a plunger anyway, so we could probably pull some of that out and displace it with some oxygen or something like that. What will happen then is the reaction will shift in the reverse environment, reverse direction. Cool. So that's what's going on there. Essentially, as we change the concentration of one of the reactants, it will shift to the other direction. So let's apply this to CO2. When we increase the concentration of carbon dioxide, what it does is move in the forward direction, but just that should say gas, and that one should say aqueous. All right, so a decrease in the concentration of carbon dioxide, gas, or AQ even actually in this case, if we go to the second equation, or an increase in the concentration of carbonic acid causes the system to move in the reverse direction. So a very good way of looking at this is CO2 plus H2O. We draw our little reaction here, and we got H2CO3 AQ. This works best if we look at this one, because they're all aqueous at this stage. So if we increase this one here, so if we, put more, inject carbon dioxide gas in, which causes the reaction to move further to this one, which brings us to this second step here, which causes this, so as this one goes up, that means that will go up. And so that's how we increase the acidity of the water. Now, if we were to heat this up, right, so that this leaves, this one here, this concentration. So as we heat it up, this concentration will go down. That will cause this concentration to go down to maintain its equilibrium. And the next video that we'll see will make it'll clarify what that looks like graphically a bit more. All right, so we can change the pressure as well. Now, very important to remember, if you change the pressure, it only affects the gases. Okay, so change in pressure only affects the gases, which means in this, of our four reactions, we're only looking at this one in this case. So your CO2 All right, we're only working on this one. So now an increase in the pressure causes the system to shift in the direction of the fewer gas molecules. So as we increase the pressure, which of these two has the fewer gas molecules? It's that way. Decreasing the pressure goes the other way. Now, if the number of gas particles on each side of the reaction is equal, then a change in pressure has no effect. So let's apply this to CO2. This is actually really important, by the way. Some of you are struggling in class with this one. So an increase, it's the fewer gas molecules. Okay, so if it's, the next video will have an example of it that's actually quite good. But basically, if these were both gases, and that one had a 1 in front of it, and that one had a 2 in front of it, then this is still the one with more gas molecules. And I'll just get rid of that because we don't want to confuse the issue any more than I already am in my shonky teaching. So let's apply this to CO2. Basically, an increase in gas pressure causes it to move forward. That makes sense. Gas is only here, so as we increase it, it goes in that direction. A decrease in pressure, so opening the can of soft drink will cause it to go in that direction because that decreases the pressure. So you get more gas. So this is where we finish it. The solubility of carbon dioxide in water is dependent upon 3 factors. That's 4. So 3 factors: temperature, pressure, concentration. All right. We've now applied Le Chatelier's principle to one reaction, and yeah, we'll look at some more in class.